This is lesson 8.3, day 3, solving trigonometric equations using trig identities. So this is the warm-up problem for the day. Go ahead and solve secant squared theta equals secant theta plus 2 over the interval 0 to 2 pi inclusive. Go ahead and pause the video, work the problem out. When you're finished, unpause and check your answer. The answers are pi over 3, pi, and 5 pi over 3. Here's a list of strategies that we've used so far to solve these trigonometric equations. Number 1, we've isolated the trig function. So that means that we treated each equation like it was an algebraic equation, and we had done either one or two-step equations, or we solved them by taking the square root. In the last lesson, we talked about setting each equation equal to 0 and then factoring. And we also used U substitution to make the problem more simple looking, to make it look more like an algebra problem or something from Algebra 1. In this lesson, we're going to rewrite using only one trigonometric equation, and we're going to use substitution by using the identities. So for example, if sine and cosine are in the same equation, or sine squared and cosine squared, we may need to use substitution to have everything written in terms of one of the trig functions. So going on here, we're going to take a look at the different trig functions and trig identities that we've covered in other sections. So a quick reminder here. We've used tangent theta and we've replaced it with sine theta over cosine theta, and I wanted to put it here as reference because you are going to have to be using that again. So now what we're going to be looking at are the Pythagorean identities. So the most basic one we talked about was sine squared theta plus cosine squared theta equals 1. And I'm not going to go into how that's derived because we've done that in another chapter, but I want to look at the other versions of this. So let me go ahead and take my pen here. So if I take this equation and I divide through by cosine squared theta, I can generate a new equation out of it. So cosine squared theta and cosine squared theta. And when we look at what this generates, go ahead and take this off here. So we've generated the equation tangent squared theta plus 1 equals secant squared theta. Now the other ones, if I go ahead and divide through by sine squared theta this time, you'll see that we generate 1 plus cotangent squared theta equals cosecant squared theta. Now, in order to use substitution for equations, I'm going to have to make sure that I have each of these solve for one of the trig identities. So I want to go ahead and just briefly show you what these look like. So if you take this first equation and you solve it for just sine theta or just cosine theta, here's what those look like. So if I isolate sine squared theta, I subtract cosine squared theta from both sides. So in other words, anywhere I see a sine squared theta in an equation, I can replace it with 1 minus cosine squared theta. And likewise, I could isolate cosine squared theta, and that would be equal to 1 minus sine squared theta. Now this one here, if I isolate tangent squared theta, I'd have to subtract 1 from both sides, and I would get that tangent squared theta is equal to secant squared theta minus 1. And of course, on this equation, the secant squared theta is already isolated. If I wanted to, I could go ahead and flip the left and right hand sides around so I can see that the left side is the isolated portion of that. And that's consistent when you look at sine squared theta equals cosine squared theta equals tangent squared theta equals and secant squared theta equals. You can use these as references for when you're solving each of these equations. And down on this last identity, let me go ahead and remove this. You can see that if you isolate cotangent squared theta, you'll subtract 1 from both sides. And of course, if I take this equation and I just switch the left and right hand side, I'll get cosecant squared theta equals cotangent squared theta plus 1. Use this as a reference list to decide which substitution that you're going to use. All right, number 1, find all solutions over the interval from 0 to 2 pi in radians for the following problem. So this will be all of the problems in this particular lesson. So number 1, we have tangent theta equals 2 sine theta, and you'll notice that we have two different trig functions in this problem. I am going to go ahead and set this equal to 0 though, and then afterwards I'm going to see if I can do some switching on this. So we have tangent theta minus 2 sine theta equals 0. Now, all of my Pythagorean identities have squares in them, so I'm actually not going to use that. I'm just going to use the idea that tangent theta is equivalent to sine theta over cosine theta. So I'm going to rewrite this. So I have sine theta over cosine theta minus 2 sine theta equals 0. Now I do have sine theta in both terms, so I'm going to go ahead and factor that out. So sine theta, and then parenthesis, 1 over cosine theta minus 2 equals 0. So now I have this in factored form, and I can use zero product property, and that says that the sine of theta equals 0, and the cosine of theta minus 2 equals 0. So now what I'm going to do is I'm going to go ahead and use my unit circle to find some of my solutions here in just a minute for this one. And over here I want to go ahead and isolate, let's see, we've got to correct that. Let's put that as 1 over cosine theta minus 2 equals 0. And underneath this I'm going to simplify, so I have 1 over cosine of theta equals 2 if I add 2 to both sides. And I'm going to solve for cosine theta, so I'm going to flip over both the left and right hand side. So I have cosine of theta equals 1/2. And so we're going to go ahead and calculate each of these. So theta equals and theta equals. I'm going to go ahead and uncover my unit circle over here. All right, so looking at my unit circle, I can see that I have a couple solutions that I've highlighted here. And so theta in this case for sine 0 is going to be 0 and pi. And over here we have pi over 3 and 5 pi over 3. So all of my solutions together written in order would be 0, pi over 3, pi, and 5 pi over 3. Number 2. So there are two options here. I have sine squared theta and cosine squared theta in the problem, and I can go ahead to choose to either replace sine squared theta or I can replace cosine squared theta. So in this problem, what I'm going to do is I'm going to go ahead and replace the cosine squared theta. So I go over to my list here and I can see that I can replace cosine squared theta with 1 minus sine squared theta. So that's what I'm going to do. So I'll have 3 sine squared theta minus parenthesis 1 minus sine squared theta equals 0. Keep in mind you're using substitution, so make sure that you use parentheses because in this case we're going to have to distribute this negative. So we have 3 sine squared theta minus 1 plus sine squared theta equals 0. And you're going to combine your like terms. So we have 4 sine squared theta minus 1 equals 0. And we're going to add 1 and divide by 4. So we're going to have sine squared theta equals 1/4. Take your square root of both of your sides here. So we have sine of theta equals plus or minus 1/2. And we're going to go up to our unit circle here and go ahead and figure out, and get this to switch here. There we go. And you can see here we've got our values that are highlighted. Get rid of that. There we go. So those are all our highlighted solutions for number 2. So we've got a couple of those. And those are all in all 4 quadrants. So we've got pi over 6 and 5 pi over 6, 7 pi over 6, and 11 pi over 6. Number 3, so I have 2 tangent squared x minus secant squared x equals 2. And in this one I could replace tangent squared x, or I could replace secant squared x. I'm going to go ahead and replace secant squared x because I like to work in tangent squared x. There is no right or wrong answer here, but this is pretty straightforward. So I'm going to replace secant squared x with tangent squared x plus 1. So 2 tangent squared x minus the quantity tangent squared x plus 1 equals 2. Distribute your negative. And we're going to simplify and set equal to 0 here. Well, we may not have to set equal to 0. Let's take a look at this. 2 tangent squared x minus 1 of them is 1 tangent squared x. So we're not going to set equal to 0. We're going to go ahead and isolate the tangent squared x and take the square root of both sides. So we get tangent of x equals plus or minus the square root of 3. And we're going to go up to our unit circle here and see what we have. There we go. And we have a number of values in all 4 quadrants. So we've got pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So number 4. So number 4 is going to require us to do a little bit of factoring as well as some replacements. Now I notice I have sine x here, and I don't have any replacement values for regular sine x, but I do have replacements for cosine squared x. So I'm going to replace cosine squared x with 1 minus sine squared x. So we have 2 parenthesis 1 minus sine squared x minus sine x minus 1 equals 0. So now I have only sine functions within this. Distribute, so 2 minus 2 sine squared x. And I'm going to go ahead and combine my like terms. So I have negative 2 sine squared x minus sine x. Make sure that's an s there. And then I have a 2 and a minus 1 that are going to give me a plus 1. And I'm going to go ahead and divide every term by this negative 1. I prefer not to work with a leading coefficient of negative. So I've got 2 sine squared x plus sine x minus 1 equals 0. And we're going to use u substitution. So we're going to let u equal sine x. So it looks a little easier and cleaner to work with, like an algebra problem. So 2u squared plus u minus 1 equals 0. So we're going to go and factor that. So we have 2u and u. And we're going to have a minus 1 and a plus 1. Set each of those factors equal to 0. The first one's going to give me u equals positive 1/2. And the second one is u equals negative 1. I'm going to replace u with sine again. So I have sine of x equals 1/2. And sine of x equals negative 1. We're going to go up to our unit circle and see if we can take a look at the values on the unit circle that work. There you go. and you'll see those highlighted values. So we have x equals, from the first one, we've got pi over 6 and 5 pi over 6. And then from the second one, we have 3 pi over 2. Okay, number 5 is a workout on your own problem. So please pause the video, work the problem out, and when you're finished, unpause it and check your answers. Number 5 has 4 solutions: pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Number 6, pause the video again and work out this problem on your own as well. When you finish, unpause the video and check your answer. Number 6 requires replacing cosine squared x with 1 minus sine squared x. It also requires you to do some factoring, so once again we did use substitution to make it a little easier to work with. And you will notice when you get your two equations for sine of x, you do get sine of x equals 2 over here on the right hand side, which is a no solution portion of the problem because the range for a sine function is -1 to 1 inclusive. So two solutions, 7 pi over 6 and 11 pi over 6. Number 7. So before I go replacing cosine squared x with a value, what I'm going to do here is see if I can do some simplifying, because I can rewrite tangent x as sine x over cosine x. So that's what I'm going to do. So I have sine x over cosine x times cosine squared x equals 0. And over here I can cancel this cosine x with one of the cosine x's here. So I have sine squared x minus sine x cosine x equals 0. I have two terms here. The greatest common factor is sine x, so I'm going to factor out a sine x. And within parentheses, I'll be left with a sine x minus cosine x equals 0. The zero product property says either the sine x equals 0 and the second one, the sine x minus cosine x equals 0. So now the second one here, what you want to do is move the cosine x over to the other side. We're not going to replace out cosine x with any relationship with sine x. Here's why. If you move it to the other side, they're asking you for which angles do the sine and cosine ratios equal each other. So all you have to do is go to the unit circle and see where that occurs. So let's go ahead and go to our unit circle. There we go. And you can see a couple of things happen here. The sine of 0 is occurring at 0 and pi. But then in quadrants 1 and quadrant 3, we have identical sine and cosine values. So our solutions here, we've got x equals 0 and pi for this one. And the second one, we've got pi over 4 and 5 pi over 4. So if we write those in order, we've got 0, pi over 4, pi, and 5 pi over 4. All right, number 8. So we've got 4 cosine squared x equals 5 minus 4 sine x. So what I'm going to do here is I'm going to start by setting this equal to 0, and then I may use substitution for this cosine squared x. So we have 4 cosine squared x. I'm going to add the 4 sine x to the left side and the right side, and I'm going to subtract the 5. And I did that last because I'd like to see my constant over here on the last term on the left side. Now cosine squared x is replaceable with 1 minus sine squared x. So that's what I'm going to use. I'm going to distribute the 4. And I'm going to go ahead and combine my like terms of 4 and negative 5. That's going to be a minus 1. And I'm going to divide through by negative 1 so I can have a positive leading coefficient. I'm going to go ahead and use u substitution, so I'm going to let u equal sine x. So I have 4u squared minus 4u plus 1 equals 0. This is a perfect square trinomial. So 4u squared is a perfect square of 2u and 2u. And then, of course, the 1 is minus 1 minus 1. So I only need one of these. So if I set 2u minus 1 equal to 0, I get u equals positive 1/2. I'm going to go ahead and replace the u with my sine of x. And then I'm going to go up to my unit circle and locate all those values where x is 1/2. You'll see that occurs in 2 places, at 5 pi over 6 and pi over 6. And those are our 2 solutions. Number 9, pause the video and work out the problem on your own. Once you've finished, unpause the video and check your answers. Number 9, your solutions are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Number 10, pause the video and work out this problem on your own. When you finish, unpause the video and check your answers. Number 10 has 4 answers: pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3.